Okay, so we're going to have a look now at the beginning of this section for you guys, which was resting on pegs or resting on the floor. And then we're also going to do hinges as well in the same lesson too. So I'm going to go straight in with this. Again, there's only 3 things that you can do here. Pardon? There's only 3 things you can do, which is resolve vertically, resolve horizontally, and take moments. Usually you take moments about the floor, but sometimes in these ones, these are the ones where you're likely to not be taking moments about the floor. So it says here that they are resting on pegs or they are resting on the floor. And we'll use this ruler that I've got here as a bit of a model. A uniform rod AB of mass 40 kilograms and length 10 meters rests with end A on rough horizontal ground. The rod rests against a smooth peg C where AC is 8 meters. The rod is in limiting equilibrium at an angle of 15 degrees to the horizontal. So I'm going to start off by drawing a diagram where I have the floor and I have the rod that is like this, and it tells me that the rod is resting on a peg that looks like this, and a peg is something that we model as being round. So what's happening here is it's like this. If we just sort of use this as an example, this is the floor that we've got here. This is the rod that is resting on it. My finger here is representing the peg. So you can see this is the representation of what's actually happening here. What do you think is wanting to happen to this beam? Bearing in mind my finger is being modeled as a smooth peg, which means that it's got no friction. What do you think this rod is wanting to do? It's wanting to slide down like this. So you already know something about if it's sliding down like this. What do you know about? Good. So we know that there is going to be, it's trying to slide this way, so there's going to be friction going in this way here. There's also going to be the normal reaction that we've got here. And because it's a uniform rod, bang in the middle, you've got your 40G. But there are some other forces here that haven't been included. What's the other force? The reaction force that is the beam resting on my finger like this, okay? You'll notice that this reaction force is normal. It is a normal reaction because my finger can only push perpendicular to the length of what that rod is. So if it's ever resting on something, it's always going to be 90 degrees to that thing that we've got there. And I'm going to call that one N, seeing as that seems to be the letter that we've been using the most in these things that we've done so far. So these are all the forces. I guess now I just need to add in some of the distances. What's the distance between here and the 40G? Good. And then the next chunk? And then the next bit? 2. So that's the setup for this kind of one that we've got here. Now that we're so good at doing the resolving forces and the moments with the ladders, we should be pretty good at doing the moments for this kind of one. Now, the best place to take moments here, because we're trying to find the magnitude of the reaction at C, which is this thing, the best place to take moments is going to be at the bottom of the rod, which is A. So I'm going to start off by taking moments about A. So 40G, let's have a look at the line of action of the 40G. And we're going to try and find this distance running along the bottom. I haven't added in this, have I? This was 15 degrees. Without having to draw a triangle, I wonder if you could tell me what this bit is here. Good, it's 5 cos 15. So the distance is 5 cos 15 and the force is 40G. So it's 40G times 5 cos 15. And that is equal to what? 8n, good, because the n is already perpendicular. The distance from the point to the line of action of the force, we've already been told that it's 8, so I can just go straight in and say that it is equal to 8n, which means that the normal reaction at C is this thing divided by 8. So we've got, what's that, 40G times 5 cos 15 divided by 8. Is that 236.65? So 237 newtons. Is that what I did in the previous time you've seen this for homework? Okay, good, because I'm rushing. Okay, now this is the bit that's different, okay? This is the part where in ladders, resolving up and down and resolving left and right was just like baby work. It was just like the forces were already doing that. So what did I do in this video before when you looked at this for homework? Good, you took this N force. At the moment, we want all of our forces to be going left and right, or we want our forces to be going up and down. So this is fine, this is fine, this is fine. This one here is not fine, and you have to split it into 2 forces that are going like this. So one of the forces has to be going up, the other one has to be going to the left. And notice how the red arrows I've drawn here have to be exactly the same as the red arrows that I've drawn here. Just to show you something that I've seen people do badly before, they have sometimes said like, oh, great, I'll split it into this one and I'll make that a right angle. Why is that a problem? It's not accurate. Yeah, and actually like this one here is not going left and right. You're only allowed to split it into ones that are going up and down and left and right. So that is not the way to do that. I saw someone do that in the other class. I won't name them. I'm not naming them. I'm not getting in trouble with them. I will be. Okay, so we now need to figure out what the angle is. Well, this one is 15 degrees. You can make a sensible guess this one is going to be 15 degrees. But just to show you why it is 15 degrees, if you imagine a triangle drawn in here, this is 15 and this is 90, which means this one here would be 90 minus 15, which is 75. This is 90, and this whole thing here needs to be 180. So it's 180 minus 75 minus 90, which also gives you 15 that goes in there. Just in case you're just not going to believe me why it's 15. So this one here is 15, which means this force running along the top is the one that's opposite. So it'll be n sine 15. And this force running along the side will be n cos 15. Now we've got to this stage here, we can carry on and do the rest of the question where we're trying to find the coefficient of friction. I'm not even sure how. Okay, well, I'm just going to do the same old, which is resolve up and down and resolve left and right. Resolving up and down, what do I get for that one, Janet, when I resolve up and down? N cos 15 equals 40g. There's one other force missing. Which side is that on, this side? Yeah, because it's the forces going up equals this one here. So R equals 40g minus n cos 15. I've already got n in my calculator here, so it's ready to go. So I can just type in that it's 40g minus n cos 15. And we get that R is 163.41188, blah, blah, blah. And now I'm going to resolve left and right. Sarah, would you do what the left and right forces are for me? Mu r equals n sine 15. So we can now see that mu is going to be equal to n sine 15 divided by r. And I've got the value of r here. I've got the value of n up here, so I can type it straight into my calculator. So let's see what that is. 236.65 sine 15 divided by the value of r, which I hope is the one stored in my calculator. And I think you get that mu is 0.375 to 3 significant figures. Is that right? I just rushed with just I was probably going to do a bit of a shahad and just use the calculator wrong, but we'll see. Luckily I haven't made his kind of rookie mistake. So again, it just seems to be following the same thing. The only thing that's different here is constructing the forces, adding the force in here that's at a perpendicular angle, recognizing it's going to be slipping to the left, so we do the friction going to the right, and having to resolve this force into those two pieces, making sure that any force you draw on is going up and down and left and right. Okay, so I'm pleased you've seen this before, because I'm looking around and everyone's just like, yeah, we know. Like, we've literally seen this example before. Okay, so the next question is a bit more challenging, and I'm going to try and explain a bit better than I did the first time why this one is more challenging. Can I go on to the next page? So this one's a bit different, and the reason it is a bit different as soon as I look at this diagram that I've got here is, and I'll talk through what's up at the top as well, is because this force that we have here is not going perpendicular. The force there is now going at an angle, which means it's going to be a bit trickier for us to do some resolving with. So it says a uniform rod AB of mass 5 kilograms and length 8 meters has its end B resting on rough horizontal ground. The rod is held in limiting equilibrium at an angle of alpha to the horizontal, where tan alpha is 3/4, by a rope attached to the rod at C. The distance AC is 1. The rope is in the same vertical plane as the rod. That just means it's exactly as it looks like in the diagram. It's not wonky. And it says the angle between the rope and the rod is beta, and the tension in the rope is T. The coefficient of friction between the rod and the ground is 2/3. The vertical component of the force exerted on the rod at B by the ground is R newtons. Wow, there's a lot of information there, but only a few things that actually need to be added to the diagram. So one of the things is we need to add in the weight. and the weight, they've said, is 5 kilograms, so the weight, is 5g, and the length is 8 meters, which means this distance is 4, this distance is 3, and they've already told us that this distance here is 1. So some of the forces, we know that there's a normal reaction that's here. Which way do we think that this rod is going to be trying to slip? It looks like it's going to be slipping to the right, which means that the friction here is going to be going to the left. Instead of putting mu r, I'm going to go straight in with 2/3 r, because I know that that's what mu is equal to. What might change about this t, newtons? What would change about this that would mean it wasn't going to slip to the right, that it would slip to the left? Can you think about how this would need to change that would make the friction flip direction? Yeah, it could be pulling, I'd rather than saying pulling upwards, anything that's kind of pulling in this direction, if the value of this beta suddenly became quite big, if it was pulling to the left, well, it would be like this kind of scenario where someone is pulling it like this, so it's going to be moving in the opposite direction. Just worth thinking about that. It's not always going to be in the same directions. Okay, so I think the first thing we're going to need to do is probably take some moments, okay? Now, this one's a little bit different to before because we've got into the habit of taking moments about this one that's at the bottom here. But actually, there's going to be a sensible place to take moments to try and find out what the value of r is. Can anybody think where's a different place? Yeah, C is going to be a really good place to take moments because we don't know anything about t. We also don't know anything about beta. And that looks like something that we're going to be doing in the next part of the question. So if we're going to begin this question by taking moments about C. So this is a little bit of a trickier kind of one to do. We're still trying to find the perpendicular distances from this point that we've got. So I'm going to start off looking at, actually I want to start off by asking which two of these 1, 2, 3 forces are working with each other and which one is going against it. The 2/3 r and the 5g are both trying to make it rotate in this direction and the r is trying to make it rotate in that direction. So I'm going to start off with the 5g and I'm going to elongate that line of action of the force and I'm trying to find its shortest distance from C to that point here. So the distance I'm actually trying to find is this distance that I have here. I'm going to just get rid of that line because it's going to make my question become a bit complicated later on. So I'm looking for that distance there. And that angle is going to be alpha. If you think of alternate angles, that's alpha and that's alpha. And the hypotenuse is 3. So the distance for that one is? Good. So it's 5g, the force, multiplied by 3 cos alpha. We've also said that the 2/3 r is working in conjunction with it. So if I were to extend that line of action of the force, and we're trying to find the shortest distance from the point, we're actually trying to find this distance that's over here. I wonder if we can find that distance without even drawing a triangle. Good. It's 7 for the hypotenuse, and it's opposite the alpha, so it's 7 sine alpha. So we get 2/3 r multiplied by 7 sine alpha. And that is going to be equal to this last one, which I think I've been doing in this green kind of colour. We're going to extend the line of action of that force, and we're trying to find the shortest distance from here to all the way over here. Anyone think they can work out what that distance is if we know this angle here is alpha? It's a 7 cos alpha for that one that we've got there. That's going to be a 7 cos alpha. I'm going to just get rid of that for what I know is going to be coming up in the diagram. So it is a r multiplied by 7 cos alpha. So you can do the same thing that we did previously because we've got a mixture of sine and cos, so we can divide by cos to get tan. So here we've got 15g, and I've divided by cos as well. And then here I've got 14 over 3 r multiplied by tan alpha because I've divided by cos, and then I've got 7r over here. Tan alpha is 3 over 4, so I've got 15g plus 14 over 3r times by 3 over 4 equals 7r. The 3's cancel, so I get 15g equals 7r minus 14 over 4r, which is 7 over 2r, I should have just said. And so r equals 30g over 7, which is just solving that last bit there. and 30g over 7 is 42. So we've got the normal reaction, and that was by taking moments, and that was a bit tricky with that bit of taking the moments there. But again, if you draw those triangles in, everything should work out fine. We're now trying to find the size of angle beta, okay? This is the bit that looked a bit confusing if you watched that bit in the video. I'm going to show you the way that I did it, which gives you an exact answer, and then Ruhan suggested a kind of shortcut way, which I'm more than happy for you to use as well. So we've already done some of these things here. We now just need to do the next bits of the question. Well, the next bits of the question we know are going to be resolving up and down and then resolving left and right. The trouble is here is this T newtons. Now, if you remember on the previous page, I said you're only allowed to try and do forces going left and right and up and down. So you have to look at this T newtons and you have to try and split it into a force that is going left and right and then a force that is going up and down. So this is the bit where the angle can be a bit more confusing because they haven't told us this angle here. They've told you the entire angle. But do we know what this angle at the bottom is? This one is alpha. So this one at the top, if the whole thing is beta and we're reducing it by alpha, this whole thing at the top is beta minus alpha. Okay, if you think about it with numbers, it probably makes a bit more sense. If the big angle is 70 and the small one is 20, then this top one is 50 because you've subtracted them. So the one that's running up the side here is T sine beta minus alpha, and the one running along the bottom is T cos beta minus alpha. And now we've got to this stage of having quite a messy diagram. You can see why I didn't put all of those lines on there before. We can resolve up and down. So what forces do we have that are going up? T sine beta minus alpha. And what else is going up? Plus R, and that's equal to 5g. We know that R is 42, so we get that T sine beta minus alpha is equal to 5g minus 42, which is 7. And if we resolve left and right, I've got left and right, I think the only forces I've got are the 2/3 R and the T cos beta minus alpha. So T cos of beta minus alpha is equal to 2/3 R, and 2/3 R is 2/3 of 42, which is 28. So we've actually done most of the hard work. We now just want to find out what the size of angle beta is using this piece of information here and this piece of information here. I'm going to do it the slightly longer way that you will have seen me do in the video, and then I'll show you the way that Ruhan suggested. I still think my way is the most mathematical way, and it is, if they ever asked you to get an exact value. What can I do with these two statements? I can divide them. If I divide them, the t's will cancel, and I will combine them into, this is number 1 here, and this is number 2. If I do number 1 divided by number 2, I would end up with tan of beta minus alpha equals 1/4. And then what we did is I know from pure maths, I can do the expansion of tan of beta minus alpha. Who thinks they know the expansion? Ahmed? Yeah, that's right though, isn't it? Yeah, good. And that is equal to 1/4. Now, the reason I'm doing it in this way is they've actually just asked for us to find out the angle beta. If they had said, find the exact value of tan beta, then you wouldn't be able to do it on a calculator. You would have to do this method. And I'm just trying to prepare you for the nastiest things they could do. Now, we know from earlier on that tan alpha was 3/4, so I can just substitute that in everywhere. And that's equal to 1/4. So I'm going to multiply both sides by 4, and I'm going to multiply this up. So when I multiply this side by 4, I get 4 tan beta minus 3/4 equals 1 plus 3/4 tan beta. Expanding out, 4 tan beta minus 3 equals 1 plus 3/4 tan beta. So when I rearrange this and I add the 3 to that side to get 4, 4 minus 3/4, my brain is not up for any maths right now. So you get 13/4 tan beta. So tan beta is 16 over 13. And then you can do the inverse tan of 16 over 13, which is beta is 50.9 degrees, okay? That's if they wanted you to come up with the exact value of tan beta, but you could have just come up with this way a little bit quicker at this stage that you've got here. Is that probably the best stage to do it? Yeah, we could actually just work out what beta minus alpha is. So we could say that beta minus alpha is equal to the inverse tan of a quarter. And we know what alpha is because alpha is the inverse tan of 3 over 4. So beta is the inverse tan of a quarter plus alpha, which is the inverse tan of 3 over 4. And when you put all of that into your calculator, you get the answer 50.9, but you wouldn't get this exact answer if they asked you to find out what tan beta was, okay? So the trickier thing about this question is this fact that they've got here, that they told you what this whole angle was instead. If the question was easy, and I think you may have seen me do this in the video as well, if the question was easy, perhaps I should have actually got this the right way around to match the question. An easier one would be if they told you about this force here, if they told you this angle, because you can just very quickly resolve it into that force and that force. The difficulty with our diagram was that they told you this entire angle there, so we had to subtract that angle, which was the same as that angle that we had. So we've got, I think, maybe about 15 minutes to try some of these questions that we have that are coming up in here. I think this first one is pretty straightforward. And then for this second one that we've got in here, I believe it again makes sense to do some moments about the part at the top of the rod instead. And for this last one, if you do want to know how to do this last one, I've videoed this for the other class when they went through it for their homework as well. So we've got about 15 minutes. I'd like you to start off with this one that we've got here, but I shall leave it on this page for you to have a look at. Okay?